Let us now prove in this video theorems 1, 2, and 3 that we saw in the overview of Cauchy sequences. I put all three theorems together as this big theorem that has three parts, A, B, and C. The first part, A, says that any metric space X, for any metric space X, when we have a convergent sequence, then it's a Cauchy sequence. The second part says that in a compact metric space, a Cauchy sequence converges to some point in X, in the space. And the last one says that in Rk, every Cauchy sequence converges. Okay, so let's get to the proof. Part A is the easiest. So for part A, if we have that the sequence is convergent, okay, that means that given epsilon bigger than 0, there exists some integer n, capital N, such that the distance between P and Pn is smaller than epsilon. This is the definition, and this is for every n bigger or equal than capital N. But now we have the triangular inequality, right? That says that if I want to show that it's Cauchy, right? So then I need to check the distance between Pn and Pm, which is less or equal than the distance from Pn to P and Pm to P. And both of these are less than epsilon. So this is 2 epsilon as long as n is bigger or equal than n, m is bigger or equal than capital N. And therefore, Pn is Cauchy. So this part is done. Now for part B, we have a Cauchy sequence in a compact metric space, and we need to show that it converges to some point in X. So here, the difficulty is that we know it converges to some point, because we don't know what is the point. Part of the proof is to figure out what the limit could be. All right, so we have our Cauchy sequence. In our compact metric space, in our compact space. Okay, and here what the trick is to define this, to define a set En that is going to consist of the terms in the sequence that are larger or equal than capital N. Now, one obvious thing these sets, as n grows, they become smaller and smaller because we are leaving more terms out. Okay, they are still very large, but as we keep taking out terms, they are growing smaller. We will use this, so it's important to keep in mind. Now, another thing that we need to keep in mind is that a sequence is Cauchy. Pn is Cauchy if and only if the diameter of these sets converges to 0 as n goes to infinity. What is the diameter of a set? The definition of diameter is the supremum of the distance between any 2 points in the set. So take 2 points, PQ, compute the distance, take the supremum among all possible choices. Okay, and this, you will agree with me, that gives you what we could call the diameter, the longest distance between elements in the set. All right. One property that I'm not going to prove, but we are going to use, is that the diameter of a set, any set, equals the diameter of the closure of the set. But you can probably believe that because we have a supremum here, right? And when we have a supremum, yeah, that goes well with the closure. This is proved in the book if you need to, if you want to go through the proof. Now, because these two are equal and Pn is Cauchy, then I know that the limit as n tends to infinity of the diameter of the closure of the En is going to be 0. Okay. And now here it's very important that we have a closed subset of a compact set of X compact. Okay, so what happens when we have a closed subset of a compact? We saw that the subset is compact itself. Okay, and this is very important. Now we have that the closure of the En is compact. Now, because we saw that the sets are decreasing, okay, we have the same thing for the closures. Okay. And once we have these two, then the intersection of all these closures of the En is going to consist of a unique point. Consists of only one point that we can call P, and it's a point of X. Okay, this is also proved in the book if you need to check. Okay, it's in chapter 3. Now this point P, this is our limit. So, well, at this point we can only say that it's a candidate to limit. So let's show that it's actually a limit. So let epsilon be given. Okay. And then you will agree with me that the diameter of the En, it will be smaller than epsilon for some, let's put it here. Sorry, not for some, for all n bigger or equal than some n0. Okay. Actually, the best way to write this down would be to say this first. So let epsilon be given, then for some n0, the diameter of the closure of the En is less than epsilon for all n bigger or equal than n0. Okay, and this is basically what we want, because the intersection, the infinite intersection, consists of one point P. That means that P belongs to all the En for every n. Okay, so that means that the distance between P and Q, which is less than the supremum of these distances, which is smaller than, which is by definition the diameter, right? And we know that it's less than epsilon. Have it here. Okay. This is going to work the distance of P and Q less than epsilon for every Q that is in the closure of En. Okay. And in particular, for the Pn. Okay, so here we have, as we needed, that the distance between P and Pn is less than epsilon, which means that the Pn converges to P. Okay. So what we have seen here is that geometrically what we have seen is that we are working very close to, there is an accumulation. Okay, there is a point P that survives everything, and then that's the limit of the sequence. And lastly, the proof of C. This is very similar. In this case, we can have a Cauchy sequence in Rk. Okay. And just define the En as before. Okay, these are the tails of the sequences. Okay, all the elements in the sequence for the indices larger than n. And you will agree with me that if n is large enough, then the diameter of the En is less than 1. Okay, because this means that the sequence is concentrating somewhere. Okay, so this means that the range of the sequence xk, okay, is the union of this En that we just found and the finite number of points xk. Okay, actually the x1 through xn. Okay, so what do we have here? So we have that the whole sequence is contained in this En and a finite number of points. So this means that the whole sequence xk is bounded. Okay, because we can take an open set that covers all the x1 through xn plus the En that covers the rest. So then the xk is bounded. And this is very important because once we have that xk is bounded, and because we know that a bounded set in Rk has compact closure, okay? With these two things together, we can find a compact set where we can apply B. Okay, and from here we conclude. Now here I want to mention the difficulty in part C. The reason why it's not obvious, doesn't follow obviously from B, is that Rk in itself is not compact because it's not bounded. Okay, so we need to go somehow. You see what we did here? We went from the Rk that is not bounded to showing that the sequence is bounded. Okay, and we did that splitting the work, taking a tail of the sequence that is contained in a ball of radius 1, and then we have a finite cloud of points that we can cover with some open set, and then that is bounded. We can cover by a bounded set, not open. that is bounded, and then if we close it, we have a compact set, and then we can apply B.